lecture is about random samples and order statistics. So this is really kind of starting to get to the end of 451 material and gives you a glimpse of some of the things that you might talk about in a 452 class. So it is typically covered in 451, but it kind of starts to move from probability into statistics. And so as a statistician, I find this lecture to be really interesting because it brings together all the things we've learned throughout the semester and starts using them to talk about some interesting statistical topics. So the first thing that we want to do today is we're going to define what a random sample is. So we're going to have a definition of a random sample. And a random sample actually has a kind of simple definition. Now that we've done all of this legwork throughout the semester, we say that if we have a series or a collection of random variables, say x1, x2, x3, up to some xn, and if these are independent and identically distributed, they are IID from some distribution, which we're generically going to denote the PDF of that as, or PMF of that as F. So here F is the PMF or PDF of some univariate distribution. And if my collection of random variables x1 to xn are all independent and identically distributed from this distribution, then we call the collection of these x sub I, which I'm just going to denote as xi, I goes 1 to n, a random sample from F, from my distribution. You could also kind of qualify this. You could call this a random sample with size n, or of size n. So a random sample is just a collection of independent, identically distributed random variables. A random sample from some distribution is a sample of II, or a collection of IID random variables from that distribution. So let's talk about some facts of a random sample. So here we have our x sub I are a random sample. Then, so my notation here is, as it was in last lecture, x tilde, the capital X tilde, is just my vector of random variables. And we could say it's x1 to xn transpose. This is a random vector. And it's a multivariate random variable. And little x tilde is some number in Rn. Okay, so this is just some notation. But if I have my collection, my random sample, which means that basically I have a random vector where the components are IID from some distribution, then I could look, for example, at the joint distribution, say f x tilde of little x tilde, right? So this is the joint distribution of my random variables, x1, x2, 3, xn, the joint PMF or PDF of these. If these things are from a random sample, what do we know? Well, first of all, we know that they're independent. So because my x sub I are, my random variables are independent, I can factor this joint PDF as the product of all of the marginals. So this is more or less synonymous with a definition of independence. Not quite the definition, but it's kind of the fundamental useful theorem of independence, which is that if I have a collection of independent random variables, I can always just factor the joint PDF into the product of the marginals. So if you recall, we have IID, random variables. So the first I is independence, which allows us to do this factorization. And the second I is identical. And then we have a D for distributed, so identically distributed, which means that the marginals are all the same. So I'm generically, right, we say F is the marginal distribution of each of these. So I actually don't need this subscript x of 1 or x2 because they all have the same marginal distribution, which we're just going to generically denote F. So this is F of x1 times F of x2 times F of x3 times F of x sub n. And of course, you can write this more compactly with product notation. This is the product, the pi for product. I goes 1 to n of f of x sub I. And so we're allowed to do this because we have identical distributions. And so this is kind of a super useful kind of fundamental fact about random samples, is that the joint distribution is just the product of the marginals, or the product of the marginal. They all have the same marginal distribution. Evaluate that each of the little x of i's. Cool. So let's go one step further. Typically what we do with a random sample is we use it to calculate a statistic. So this is what you do in a statistics class, is you take a random sample, you collect a random sample, and then you use it to calculate a statistic to inform you about something in which you're interested. So let's give a definition of what a statistic is. So if, again, my collection of my x sub I are a random sample, I'm just going to say RS for random sample, and T is a function that goes from Rn to R, let's say D, then T of my random vector, my collection of elements in my random sample, is called a statistic. And that's actually the full definition of a statistic. It's a little bit unsatisfying. Statistic actually doesn't have, or has a very broad meaning. It's not a very kind of convoluted, complicated definition. A statistic is just a function of a random sample. So typically, we could say D is less than n, e.g., for example, often D is equal to 1. D being less than n is kind of says that our function summarizes our random sample. If D were bigger than n, we'd go from n samples to some n dimension or D dimensional statistic that has more components than data, which is a bit weird. Typically, like a univariate statistic, you just summarize it into one number. So we could look at some examples. Probably the most famous example would be the arithmetic mean. So our arithmetic mean, x bar, right, is 1 over number of samples times the sum of my samples. Right? That's the arithmetic mean. This is a statistic. Here, our function t takes in some element of r sub n and spits out 1 over n times the sum of the elements. And so my random, my statistic would be t of my random vector. This thing here, given this definition of t, you could write this as t of my random vector, replacing the kind of real numbers with random variables, as we've done before. And so here, d is equal to 1, right? I'm just going from n-dimensional input, x tilde, to just one number, which is 1 over n times the sum of the elements of the vector. And so not surprisingly, the arithmetic mean is a statistic. But now we've had this whole class on probability, and so you could ask things about the arithmetic mean. If I know something about the distribution, for example, of my x sub i's, maybe they're a random sample from some known distribution, what do I know about my arithmetic mean? We kind of have the tools now to talk about some of this. This statistic, this arithmetic mean, is a function of those random variables. And we've talked a lot about functions. We've talked a lot about transformations of random variables. And this is why we focus so much on transformations of random variables, because statistics are just transformations or functions of a certain kind of random variable, a random sample. Of course, there are other examples of statistics that we could talk about. If you've taken a intro statistics class, you may have come across, for example, the sample variance. Typically, it's denoted s squared, and maybe it'll look something like 1 over n minus 1, some I goes 1 to n, and what is it? It would be x sub I minus x bar, our arithmetic mean, squared. So that is kind of typically the definition of a sample variance, and there's going to be some t. Again, it's a univariate, it's a one-dimensional statistic. Takes in my random sample, my x sub i's, and computes some function of them that just spits out a single kind of univariate random variable. And there's some function t, you could write it down. That's not too surprising what it is. I just basically replace my random variables with real numbers. So there's another example. Today we're going to talk kind of as an introduction to some of these ideas. We're going to talk about order statistics. As examples of some statistics. We're going to talk about them. So for example, let's say x1. So I'm putting parens around the subscript 1 to note that this is the minimum of my x sub I. Alternatively, some notation for this would be min over I goes 1 to n of my x sub I. So I collect my random sample, it's going to be the smallest value. Of course, you could write the maximum, which is denoted x sub n. Again, parens around my n to note that this is not the nth one in the sequence, but is the maximum of my x sub I. Collection of my x sub I here. And alternatively, people will denote this as max. I goes 1 to n, my x sub I. Those are kind of order statistics that people are familiar with. We'll talk about those today, but we'll also talk about x sub r, which is called the rth order statistic, which is the rth smallest value among my x sub I. So it's a generalization of minimum maximum. It's the min is the smallest, is the first smallest, the rth is the rth smallest, the n, it would be the nth smallest, or it's called maximum. And that's, again, typically the notation is x sub r with parens around my r. So order statistics themselves are interesting, but of course you can combine them to make other interesting statistics. For example, you could talk about the range of your data. So I could say R is going to be the range, and the range of my data is typically the maximum minus the minimum, which we now know is xn minus x1. Other things that people talk about are the median of data. So maybe M is my median, and this typically is either if the number of samples is odd, then my median is x sub n plus 1 over 2. So it's kind of the middle value. It's the n plus 1 over 2th order statistic, or if n is even, typically this is just the arithmetic mean of the two middle ones. All right, there is no exact middle one unless it's odd, but if it's even, we just kind of take a mean of the first of the middle two, and that's how you write that. Which would be n over 2 would be one of the middle ones, and n over 2 plus 1 would be the other one, and then so you just take the mean of those, and that's kind of how people talk about median. So before we start talking about some of these statistics, we're going to define something called the sampling distribution. Of a statistic. So this is often, let's say, like an intro stats class, we talk about the sampling distribution of X bar, the sampling distribution of something, of the population, of the p hat, estimate of the population proportion. The term sampling distribution is actually not used too much in kind of advanced upper level statistics courses because it's a little bit redundant, but we'll define it here just to make the connection to the intro stats course. The sampling distribution of a statistic t, or t of x tilde, is simply the distribution of my statistic, t of x tilde. Right, so the statistic here, if, for example, d is equal to 1, this is a univariate random variable. And it's a random variable, it's a univariate random variable. It has a distribution, just like every other univariate random variable has means and variances and MGX and all the fun stuff we talked about. So typically when people talk about the sampling distribution of, say, X bar or some other statistic t, what they mean is the distribution of that typically univariate random variable. This term isn't used too much in kind of upper level statistics courses because it's pretty redundant. You can just talk about the distribution of the statistic. And the statistic is a random variable, it has a distribution. So you don't really need this word sampling, but it's used in kind of intro stats courses to distinguish between the distribution of the data, in our case that would be the distribution of the random sample, little f, and the distribution of the statistic, which can be very different depending on the statistic and the underlying data. So let's talk about some examples of some sampling distributions or some distributions of some statistics. So kind of for the rest of this lecture, we're going to talk about order statistics. It's a great topic to kind of get familiar with some of these ideas. So henceforth, our collection of x sub I are a random sample. And for example, we could look at the minimum. Okay, so we could say the minimum x1, right? So the minimum over all values, over all random variables, x sub I. And we could say, what is the distribution, that is the PMF or PDF of my minimum? We've actually seen some suggested problems that hint at how to go about this. And so there's a kind of trick with the minimum and the maximum. For the minimum, if I look at, so the minimum is a univariate random variable. I take all n of my samples and I just pick the smallest one. And that smallest value is going to have some distribution depending on my underlying data. And I could ask, for example, what is the probability that my minimum is bigger than some value t? So there are kind of two tricks to answer this question. This is going to get to either PMF or PDF of, we'll get the CDF first, and then in the continuous case, we can get the PDF. But this is going to get us to getting kind of talking about the distribution. So if I look at the probability that the minimum is bigger than t. If the minimum is bigger than t, that means all of my random variables have to be bigger than t. That means x1 has to be bigger than t, x2 has to be bigger than t, and all the way up to xn has to be bigger than t, right? The smallest one is bigger than some value. They're all bigger than the value. Because the smallest one is above that threshold, and everything else is bigger than that. So this is the first trick, is to notice that if the minimum is bigger than something, it means all the random variables are bigger than something. And if I have a random sample, my x sub i's are independent, and so I can just factor this. This is the probability x1 is bigger than t, times the probability x2 is bigger than t, etc., times the probability that x sub n is bigger than t. And so this is justified by independence. And we could kind of simplify the notation. I could write this as the product I goes 1 to n, the probability that x sub I is bigger than t. Now, the probability that x sub I is bigger than t, this is going to be 1 minus the CDF of x sub I at t. Right? The CDF would be the probability x sub I is less than t, or less than or equal to t. And they're all identically distributed. So they all have the same CDF, so we can generically denote f is the CDF of any x sub I, right? They all are, there's a random sample, so they all have the same marginal distribution, and so f is the CDF of any of them. And so we could rewrite this as the product 1 to n of 1 minus f of t. Notice at this point we've gotten rid of any dependence on I, because they all have that same, they're all going to have the same value if the probability any of them is bigger than some fixed value t. And so this is just 1 minus f of t to the nth power. So what we've derived here is that the probability of the minimum is bigger than t is 1 minus the CDF, kind of the marginal CDF, to the nth power. And so if I want to calculate, say, well, let's say that I want to calculate the probability that the minimum is less than or equal to some value t, I would just take 1 minus, probability is bigger than that, so it's 1 minus f of t to the nth power. And of course, the probability that x sub 1 is less than or equal to t is the CDF of x1. So write f, capital F, x sub 1 as the CDF at t. Right? The CDF of x1 is just, the minimum is just some univariate random variable. The CDF is probability it's less than or equal to some value t. And we have just shown that that is this expression, 1 minus f of t to the n. And so we were able to derive this for every any possible marginal distribution f, right? Now, if I look at continuous random variables, I could go one step further, because I know that the PDF of x1 should be the derivative of the CDF. And so I could take a derivative of this, and what would I get? I just take a derivative of 1 minus f of t to the n. And there's a little chain rule in action here. But the one goes away, minus 1 minus f of t. I guess I should bring down the n. So minus n, brought down the n. This is the n minus 1 power. And then I have the chain rule, derivative of the inner, which is a minus derivative of the inner is a minus df dt. But of course, we'll get some cancellations. The minus and the minus cancel. I get n 1 minus f of t to the n minus 1. And df dt is just little f of t. And so that's for at least for the continuous case, that is the PDF. And for the discrete case, you can get the CDF. But for the continuous case, you can get the PDF. And capital F is the marginal CDF of any of my f sub i's, and little f is the marginal PDF of any of my x sub i's. But that's the formula for continuous random variables. If I have a random sample and they have a marginal PDF of little f and a marginal CDF of capital F, the PDF of the minimum is n times 1 minus the CDF to the n minus 1 power times the PDF. So that's nice. So that is kind of our first, as it were, sampling distribution. If I give you a distribution of the random sample, and we'll look at an example, but if I give you a distribution of my random sample, they're all from a uniform distribution. Then I would know capital F, I would know little f, and you would actually get a formula for this, and this would tell you how the minimum is distributed there. Before we do an example, we can look at the maximum. We're going to go through this real quick because it's basically kind of a similar process. It's actually even a little easier. So let's get the PDF for the maximum, x of n, with parens around it. The CDF for the maximum is the probability that my maximum is less than or equal to some value t. And as in the minimum case, we can have a similar thing where we can say if the maximum is less than some value t, all of them have to be less than the value t. So the probability the maximum is less than some value t is the probability that all of them, x1 to xn, are all less than some value t, because the maximum is less than that and they're all less than the maximum. By independence, I can factor this. If I have a random sample, they're independent, so I can factor this as a product. And this is just the marginal CDF of each of them. They all have a marginal CDF of capital F, and it's the marginal CDF at t, right? X of 1 is just a univariate random variable. The probability is less than or equal to t is just capital F of t. And so what I get is capital F of t to the nth power. So that is the CDF of the maximum. If I look at continuous random variables, for discrete, that's kind of where we stop. If I look at continuous, again, I'll get that if I want to get the PDF of my maximum at some value t, this is the PDF of my, the CDF of my maximum, the derivative of the CDF of the maximum, right? The PDF for the maximum is derivative of the CDF. It's all just a univariate random variable. It's just a fancier random variable. So I take the derivative of this thing, and this is really easy. It's n f of t to the n minus 1, and then I have to do chain rule. I have to take the derivative of f of t, but the derivative of f of t, capital F, is little f of t. And that gives me the distribution of the maximum for a random sample. So let's stop here and look at an example. I think this would be illustrative. Example. So let's say our x of I are a random sample from an exponential distribution with a rate parameter lambda. So when I write x of I or IID exponential lambda, I'm saying there's n of them kind of generically, and this is kind of my lazy notation. x1 to xn or IID exponential lambda. That is a random sample, right? We said if you go back up to the definition of a random sample, it is just a collection of IID random variables. And we know that the kind of marginal, the PDF of any of these little x of i's is lambda e to the negative lambda x, just follows an exponential. This is for x bigger than 0. And the CDF, well, you might not remember, you could derive it or you could look it up, is 1 minus e to the negative lambda x, again, for x bigger than 0. And so I could say, okay, what about the let's say minimum? What do I know about the minimum? If I have random variables, I take a random sample of n of these random variables from an exponential distribution, and I say, okay, I'm going to do this, and then each time I'm going to look at the minimum value. What do I know about the minimum? What's its distribution? What do I expect it to be, right? Certainly, so what do we kind of know, right? Certainly all the x of i's are positive, it should be positive, but it's going to have some distribution. It's going to, it's going to take on some values more likely than other values, etc., right? And that's the whole course, right, is to talk about what goes on here. And luckily, we've derived, these are all continuous, and so we can get a PDF. And our formula was, it was n times 1 minus f of t to the n minus 1 times little f t. And so we can plug in. Capital F t is 1 minus e to the negative lambda x, so 1 minus that is just e to the negative lambda x, all to the n minus 1 power. And little f is, I guess x in this case should be t, right? We're plugging in t, not x. Little f is just lambda e to the negative lambda t. So this is kind of implicitly for t bigger than 0. T less than 0 is not going to have any positive density. And you could actually simplify this. How can we simplify this? We could say it's n lambda, and then we could combine with e to the negative lambda t times n minus 1 times e to the negative lambda t. Of course, the product of exponentials is the exponential of the sum. And so it's n minus 1 plus it's n minus 1 negative lambda t's plus another lambda t. So we could write it this way. I'm actually going to write it like this. It's n lambda times t. And the reason I'm going to write it like that, no prevalent, just some algebra. The reason I write it like that is I notice that this is a PDF of an exponential distribution, but instead of rate parameter lambda, I have a rate parameter of n times lambda, right? It'd be lambda e to the negative lambda t, but now it's n lambda times e to the negative n lambda t. And so what this says, the punchline here, is that my minimum of my exponentials has another exponential distribution, but instead of parameter lambda, it has a parameter n lambda. And so that's a cute little fact. It doesn't always work out that these things have nice named distributions. As you see for the maximum, we'll do the maximum in a second. It's not going to be anything we kind of have a name for. It has some PDF and it is what it is, but we really have a name for it. But it turns out that the minimum of an exponential, the minimum of a random sample of exponential, is again exponential, but my rate parameter is lambda. There's n lambda instead of lambda. And we can play the same game for the maximum. Look at the maximum. Our formula said that the PDF of the maximum was n times f of t, capital F of t, to the n minus 1 times little f of t. And in this case, it's n times 1 minus e to the negative lambda t, all to the power n minus 1 times lambda e to the negative lambda t. And that's really actually kind of as simple as you really care to get it. There is no name for this distribution that I know, but it is the valid PDF. And you could say, I could say, what's the expected value of my maximum? And I would use this PDF to calculate an expected value in kind of the classic way. It involved maybe a nasty integral, but it's doable. Certainly Wolfram Alpha can tell us the answer. And so you can calculate all sorts of probability statements or expectation or variances of my maximum. And so I could make statements about my maximum, what I expect the maximum to be for a random sample of exponential. Very easy. I know what I can say about the minimum, for example. I could say that the expected value of my minimum, if I take a random sample of exponentials and then get the minimum, I expect to get a value of n times lambda as my minimum. And you could make similar statements. I don't know what the expected value of this distribution is off the top of my head, but you could do it. So that's the minimum and the maximum. Those are the easy cases. What we want to talk about is now kind of more general order statistics. And so we had looked at, we had named what we said was x sub r. Brackets around my r to denote that this is the rth order statistic. That is, it's the rth smallest among x1 to xn, among my random sample. So the way you could envision this is you draw a random sample according to the distribution, you write down the minimum. Or you write down the rth smallest one. You order them, and then you write down the rth smallest one. And it's possible that any of these, so one thing to keep in mind is the difference between x sub r with the brackets around it, that's my rth order statistic, and just the rth of my sample. Totally different things, right? Any of my random sample could be the rth smallest, depending on how my draw happens. And so this x sub r is really kind of a function of all of these. It's not really like the minimum is not always the first one, right? X sub 1 is different than, right? Like x sub 1, not the same thing as the first of my random sample, right? X sub 1, the last one could be the smallest one. Not necessarily, x sub 1 could be any of these. So there's a difference between with the bracket, with the parens, which the order statistic without the parens is just in the sequence, right? And they're all kind of, the sequence, the random sample, they're all kind of equivalent, right? They're all independent, they all have the same distribution. So they're not really they're very kind of similar to each other, whereas the order statistics can be very different. The distribution, the minimum, the maximum are very different. Okay, so the theorem we're going to write is that if my x sub I are continuous, then we can basically generalize. We had derived formulas up above here. We had derived one for the maximum. We had derived one here for the minimum. We can generalize this into the PDF for the rth order statistic. The PDF for x sub r at some value, let's say t, has the following form. It is n factorial over r minus 1 factorial, n minus r factorial, times capital F to the power r minus 1, 1 minus capital F to the power n minus r, times the marginal PDF. So that's the formula. Again, you don't need to memorize it, but we'll use it. And we could actually see why this is true. But it's a little bit of a doozy formula. It generalizes, so if you plug in r is equal to 1 or r is equal to n, you'll get the formula that we had previously derived for the minimum and the maximum. Unfortunately, the argument to derive that PDF is not quite as easy as it was in the minimum and the maximum. The max have these nice properties. So again, here, this is the CDF of the x sub I, and little f is the PDF of any of these x sub I. Marginally, they all have the same distribution. They are a random sample. So I'm not going to do a kind of really, really formal proof, but I'm going to kind of make an argument for why this is the correct formula. So let's draw a picture up top here. This is going to be my number line. And my rth order statistic is going to lie somewhere there. and I want to look at the density, probability density that my arithmetic statistic at t. So I could think about some interval t to t plus delta t, for example, and I could look at the probability t x of r is in that interval, and I could shrink delta t to 0. So I could just shrink that interval. That is my PDF, the density that the arithmetic statistic ends up at t, you can think of as kind of a limit as delta t goes to 0 of the probability that x of r is in some interval t to t plus delta t. So it's basically this, which looks a lot like a derivative, and it's basically, we know that this is the derivative of the CDF, but you could also think of it as this way, as this kind of as this limiting expression. The density is kind of the probability as we shrink to this interval down, 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 down. It's kind of like a derivative type notation. And we could talk about what the probability that x of r is in some interval, shrink the interval down, and that is going to give us our density. So, so let's look at what that is, right? So we want x of r to be in this interval t to t plus delta t, which means that the rth smallest is in this interval, and we're going to have r minus 1 smaller values below t, and n minus r values larger, right? So that we have r minus 1 smaller, n minus 1 larger, and 1 x of r in that interval. That's what it means to be the arithmetic statistic. It's the rth smallest. If r minus 1 smaller, then you have x of r, and then you have 1's larger. Notice that n minus r plus r minus 1 plus 1 will give us back all n of them. And what I'm basically going to argue is that in the limiting expression, the probability that x of r is in this interval is basically the probability that any of my random variables is in that interval. Like x of r, it's the probability I'm going to have one of them. It's the probability that I have one of my random variables in this interval, and then the limit, that's just going to be the density at t. The probability I have r minus 1 smaller than t is the CDF to the r minus 1 power. That is, the probability of any of my random variables in my random sample are less than t, less than or equal to t would be f of t. But if they're independent, I have r minus 1 of them, so it should be f of t to the r minus 1. And by a similar argument, this would be the probability of n minus r larger. Probability any of my random sample is larger than well, let's just say t, is going to be basically 1 minus f of t. As this interval goes to 0, this is going to be true. And because I have n minus r of them, they're independent, I can just say that's 1 minus f of t to the n minus r. So that's the kind of initial argument, right? You could write it kind of a little bit more formally, but there's not a huge reason to do that. Basically, to argue that, well, we can write it out, right? So a little more formally, this would be, really, this should be t plus delta t, right? Because we want them bigger than t plus delta t. And otherwise, that's okay. And so this probability would be f of t to the r minus 1. So I'm going to write at the top here, this probability, f of t to the r minus 1. Really, this is going to be the probability that x of r is in this interval is the probability that it's going to be f of t plus delta t minus f of t, right? That's the probability it's less than equal to t plus delta t minus the probability it's less than t. And then the probability that we have this n minus r larger is 1 minus f of t plus delta t to the n minus r, okay? And so that's the top there, basically. And we're going to divide through by delta t. We have to be a little careful because this is not quite exactly right. Let's expand this out a little bit. What we have to account for is that I can choose any of my x sub I to be the rth order statistic, right? There's a difference between the rth order statistic and the x sub I, as we said before. So what I want to do is I'm going to choose, I have n ways of choosing which of my x sub I ends up as the rth smallest. And then I'm going to choose from the remaining n minus 1, I'm going to choose r minus 1 to be smaller, and then the remaining n minus r are going to be larger. So there's actually a bunch of ways to do this. It could be that the first one is the rth order statistic, the second one is the rth order statistic, the third one is, and there's a bunch of ways to choose which ones of my x sub I are smaller and which ones are larger. And the way to do that is there are n ways to choose which is the rth smallest, and then there are n minus 1 choose r minus 1 to choose which ones are smaller. Okay, so this would be kind of the proper expression for the setup I have here. And then basically we're just going to take a limit, right? So really on the outside here we have the limit as delta t goes to 0. The n times n minus 1 choose r minus 1 is n times n minus 1 factorial over r minus 1 factorial n minus 1 minus r minus 1 factorial. And f of t doesn't depend on delta t, that can come out. So f of t to the r minus 1. As I send delta t to 0, this last part of the expression just becomes 1 minus f of, well, let's actually move it over here. It's 1 minus f of t, right? Everything's continuous, so that's okay. And if I kind of block off this part here, that is basically the derivative. This is going to basically be df dt, and we know that the derivative of df dt is little f of t. And so our final formula then is n times n minus 1 factorial, which we can write as n factorial, over r minus 1 factorial. N minus 1 minus r minus 1 just becomes n minus r factorial. We get f of t to the r minus 1. We can rearrange it, say 1 minus f of t to the n minus r times little f of t. And that is exactly what I'd written above. This was our theorem. N factorial over r minus 1, n minus r factorial times CDF to the r minus 1 minus CDF to n minus r times the PDF. So that's cool. And that gives us our formula. It's a little bit of a hand-wavy proof, but that's okay. Let's look at some examples, right? Again, you don't need to memorize it or memorize the proof. You should know how to apply it. So let's look at an example. If I have a random sample of x sub i's that are IID 0, 1, right? My PDF of uniforms is just 1, as long as t is between 0 and 1. And my CDF is just t, as long as we're between 0 and 1, right? That's what it means to be uniform. And so if I plug in my formula, my distribution of my rth smallest is, my rth order statistic is n factorial over r minus 1 factorial n minus r factorial, f of t to the r minus 1, 1 minus f of t to the n minus r, little f of t. And of course we can just plug in for what these things actually are. So my factorials out front don't change. F of t is just t, so t to the r minus 1. 1 minus f of t is 1 minus t to the n minus r. And little f is just 1. This thing is just 1, so we don't even write it. And this is as long as t is between 0 and 1. And what we can say is that we can notice that this, which is our PDF of the rth order statistic given a uniform random sample, we notice that this thing is a beta distribution. Basically a beta distribution, right? Beta is something out front involving gamma functions, factorials. X to the some power 1 minus x to something, right? Here we have t instead of x. And it specifically, this shows us that x of r, if you figure out how to match up the parameters, it shows us that x of r has a beta distribution with parameters r and n minus r plus 1. So this is true for the uniform, right? It won't be true for other distributions, but for uniform random variables, our order statistic has a beta. So the minimum has beta, the maximum has beta, and all the order statistics in between have beta distributions. Okay. So now that we've talked about the kind of distributions of the order statistics themselves, we had this theorem that said, okay, if I have the order statistic, what's its PDF? We can ramp up the fun here and say, well, what if I have two order statistics? What would the joint distribution of these order statistics be? So let's look at that. And there's a theorem for it. Again, nothing you need to memorize. I'll give it to you on the final. But we can talk about the joint distribution of order statistics. And we'll only talk about, well, we won't talk about joint of like 3. We'll just talk about 2 at a time. You could do, say, 3 order statistics, but that's going to start to get real complicated. So here we're going to have 2 numbers, r and s. R is going to be less than s. And consider the 2 order statistics, x sub r and x sub s, right? So here, note that r is less than s. This is, by definition, means that x sub r is less than x sub s, right? Because x sub r is the rth smallest, and x sub s is the s smallest. The s smallest. If r is less than s, say r is 2 and s is 4, the second smallest is smaller than the fourth smallest. I'm going to write out the formula. So what we want to look at is the joint of xr and xs, right? These are univariate random variables, and they have some joint distribution. Not particularly nice, but we're going to look at the joint at 2 values, right? So it's the joint of xr and xs at 2 values. Dummy variables, doesn't matter what you pick. We're going to call them u and v in this case. The formula, I'm going to take 2 lines here, is the following. And it's going to look similar to our univariate formula, but it's going to be a lot more complicated. Well, a little bit more complicated. It's n factorial over r minus 1 factorial, s minus r minus 1 factorial, n minus s factorial. Times, so we're going to write in the next line, times f of u, the marginal CDF, power r minus 1, f of v minus f of u, so it's f of v minus f of u to the s minus r minus 1, times 1 minus f of v to n minus s, times f of u, times little f of u, times little f of s. So that is the formula. It's quite a lot. It has a similar flavor to the univariate case, but a lot more terms in it. And again, nothing you have to memorize. I'm going to make a kind of real quick heuristic argument, similar to what I said what I did in the univariate case. Let's see if we can do this in like 1 or 2 lines, right? So this is the density that the rth order statistic is at u and the x order statistic is at v. Again, I'm talking about continuous random variables, so we have a density. So we have some value u, and that should be less than the value v, right? If v is less than u, the density is 0. We can't have the higher order statistic be smaller than the smaller order statistic. So if we have u and v, and at u here, we should have the rth order statistic. At v, we should have the xth order statistic. That means there should be r minus 1 smaller than u. Between u and v, there should be whatever the difference is, s minus r minus 1, between u and v. And bigger than v, we should have whatever the remaining is, right? It should be n minus s, bigger. And we have 1 at u, 1 kind of at v, r minus 1 smaller, s minus r between, and n minus s above. And so we could play the same kind of game with the limiting arguments, and we would say that the density is going to work out where we're going to have a component of the density of the xr of one of them being at u, one of them being at v, and then we're going to have r minus 1 smaller than u, so we get f of u to the r minus 1, n minus s of them bigger than v, so that's 1 minus f of v to the n minus s, and between, the probability that between u and v is f of v minus f of u, and how many do we have between? We have s minus r minus 1 of them between. And so basically you get that product. You have to account for how many ways I can rearrange the random variables, and that gives us all those factorials out front. So in the same way, I can kind of permute around my random variables and get the same order statistics for some permutations. Not all permutations. So we have all permutations would be n factorial, but we have to adjust for some of them that don't actually give us a different kind of different random variables being different order statistics. But that's the formula in any case. So again, if we revisit our example, again, where our x sub I are IID uniform 0, 1, then in this case, we get the joint between xr and xs at u and v to be, well, let's plug in the formula. It's n factorial over r minus 1 factorial, n minus s factorial, s minus r minus 1 factorial. And in the formula, it's the CDF to the r minus 1. Well, the CDF is what of a uniform is just, right, f of t is t, and little f of t is always 1, as long as we're between 0 and 1. So that's kind of the fact to remember. So capital F of t will just give us u to the r minus 1. So that's f of u to the r minus 1. Difference, f of v minus f of u is just v minus u to the, well, what's our power there? S minus r minus 1. And 1 minus f of v is 1 minus v. And the power is n minus s. And that's just plugging in the formula, but that would give us the joint distribution. If I had uniform random variables, that would give us the joint distribution of our order statistics. So why might we want to look at the joint distribution of order statistics? Because there are some interesting statistics we can define looking at joint. That can be, and we can get the distribution of these statistics using this joint. For example, let's just get to the point. I can look at a range, right? The range is the maximum minus the minimum. We haven't derived a formula for the range, but the range is just a function, a transformation of two order statistics, the maximum and the minimum. So we could do a bivariate transformation. If I want to say what is the distribution of my range, I could do a bivariate transformation to get the distribution of R. So we're going to have a transformation. One of the transformations is going to be R, which is max minus the min, the range. We need another, because in bivariate transformations, we always have to go from two random variables to two other random variables. So we're going to find another one, which we're going to call just a dummy transformation. We're going to find V. So normally we have U and V. Here we're going to have R and V. V is just going to be the minimum. And what we're going to do is we're going to go from the joint of x1 and xn, using our formula that we derived here, do a bivariate transformation to get the joint of the range and the minimum, and then marginalize out the range. Right, just get the marginal of the range of R, right? So typically we call this U or R, and that will give us the distribution of the range. So this is just a kind of classic bivariate transformation problem with more complicated PDF, right? So first we want the inverse transformation. And so obviously the inverse, G2 inverse of the minimum and the maximum is just V, right? I'm sorry, G1, G1 inverse, sorry, right? So I go from, right, let's say x1, comma x of n. I transform under some function g to r and b, two new random variables, right? So x1 and xn go to r. If I want the inverse transformation, to go back, I want g inverse. So I'm going to get the component functions of g inverse, which goes from, which goes this way, right? And if I want to get back x1, all I have to do is look at b. So g1 inverse is v, and g2 inverse of, I guess it shouldn't be of x1 and xn, that's why I'm confused here. The inverse function takes u and v, right? So the inverse function takes u and v and spits out the components, the original components. So x1 is g1 inverse, which just gives me b, because b is x1. G2 inverse should give me back the maximum from u and v. So G2 inverse is say, how do I get the maximum? If I know u and v, how do I get x of n? Well, I could take, what could I do? I could take r and add v. So it should be, I guess I was calling these r and v, not u and v. It would be r plus v. And that would give me my other component maximum, or other component inverse function. And my Jacobian function, my Jacobian matrix, is obviously the derivatives. So the derivative of the inverse, right? This thing is the matrix of partial derivatives of my two component functions of my inverse function. So the derivative of g1 inverse with respect to r and b, derivative with respect to r is just 0, derivative with respect to b is 1. And the derivatives of g2 inverse with respect to r and b is just 1 and 1, right? Because it's just r plus b. And so the absolute value of the determinant of my Jacobian should just give me what? 1. Now it's negative. Determinant is negative 1, and the absolute value is 1. So what we should now be familiar with is our bivariate transformations. If I want the joint of r and b at some values, let's say r and little b, this is the joint of x1 and xn, the min and the max, but now evaluated at the inverse, the first one being v and the second one being r plus v, v and r plus v, times this 1 times 1. Of course, multiplying by 1 doesn't do anything. So the reason I want my joint, I want to know something about the joint of order statistics, is now I can use my formula for the joint of order statistics. And I actually derived that in the previous problem, but instead of plugging in u and v, I'm plugging in v and r plus v, right? So in this previous part, we had got this joint here of the min and the max, and we're just going to plug in the inverse functions, right? So we had generically got, let's just as an aside here, we generically got the joint for xr and xs, but let's get the joint for x1 and xn. Let's say at values a and b, according to a formula, and I'll let you work out. This is going to be n times n minus 1 times f of b minus f of a to the n minus 2 times f of a times f of b. Okay, so I'm going to skip the steps here. this, which I've just derived, is literally taking this formula here and plugging in, instead of r and s, it's 1 and n. And it really simplifies a lot because many of these terms go away. And what we get when you simplify it is it's n times n minus 1 times f of b minus f of a to the n minus 2 times little f a times little f b. But it's just plugging into that formula. And that will allow me to continue on my problem here. Now I'm plugging into this thing, v and r plus b, so it's n times n minus 1. And f in this case, in the case of uniform, all right, in the case of uniform, we said that this was just, that the f is just, f of b is b and f of a is a, so this is just b minus a to the n minus 2, all right? Here we'd use the letters v and u. We don't want to reuse those, but and we're plugging in v and r plus b, so it's let's just get this correct here. It is for b, we plug in r plus b minus b to n minus 2, and then f here in this case is just 1. These f's are just 1 because we have we're assuming uniform, right? We go back up, we're assuming, we're kind of continuing here where our x of I are IID uniform 0, 1. So actually we don't even need these in our formula. And this now is f of r b. So this is the joint of the range, which is the maximum minus the minimum, and v, which is just the minimum. So let's put a box around this. This is the joint of the range and the minimum. We don't actually want this. And in fact, we can even simplify this a little bit, right? N by n minus 1, r plus b minus b. This is just going to give us r to the n minus 2. So this is even simpler. We don't actually want the joint of the range and the minimum. We just want the range. But now that we have the joint and the range and the minimum, we can just marginalize, get rid of the minimum, and just integrate across b to get the distribution of r, or the PDF of r. All right. So if I want just the marginal of the range, f of r, what I do is I integrate this joint. Now this joint actually doesn't involve b in a really obvious way. I integrate with respect to b. I just have to get my limits of integration correct, right? So I'm integrating out v, which is the minimum. So what is v allowed to be? Well, I know my random variables all are between 0 and 1. And so certainly my minimum could be 0. So the lower limit of integration is 0. And so it could be that my minimum is here, and then my maximum, or sorry, my range, if my range r is some value r, that would be my maximum would be over here. So that's one limit. Now, how big could x of 1 be? I could push x of 1 up to a certain extent, but I can't push it past a certain point, because I know if I push x of 1 to be here, then I know my range is r, and so my maximum could end up at most over at 1. So if my maximum were at 1, the biggest my maximum could be is 1, which means the biggest, if I know the range is r, the biggest my minimum could be is going to be basically 1 minus r. So when I do this, the upper limit of integration should be 1 minus r, because it's the biggest that my minimum could be, right? We're talking about v here. We're trying to figure out the range of v, which is my minimum, go from 0 to 1 minus the range, right? You can't go all the way up to 1, because we know the range is some non-zero value r. But this is just an integral now. It's actually not too bad of an integral because it doesn't really involve v, right? I can vector out my n minus 1 r to the n minus 2, and I just get the integral from 0 to 1 minus r dv, which just gives me n times n minus 1 at r to the n minus 2 times 1 minus r. So that, finally, after all that work, gives me my range, my marginal distribution of the range. And what you might notice is that in the case of uniform, the range is also a beta random variable, but it's a really simple beta random variable. The range is a beta n2. So that was a real kind of tour de force there of a lot of these topics, but we kind of combined a bunch of stuff that we covered in the class so far, right? So we talked about basically what a random sample was today. And basically the key fact of random sample is that the joint is just the product of a bunch of identical marginals. Statistic is just a function of a random variable, and today we looked at some statistics. And we wanted to look at the sampling distribution, or just the distribution of the statistics. Statistics are just other random variables, typically other univariate random variables, which are functions of my random sample. And so we looked at the distribution of the minimum, which you can kind of cleverly get, or the distribution of the maximum. We looked at some examples from the exponential, and then we look more generally at the order statistics. You can get the marginal distribution of any order statistic. Or you can get the joint. We also did after doing some examples, we got the joint of the order statistics. And this, for example, allows us to get the distribution of the range, because the range is just a function of the order statistics. And so if I know the joint distribution of the min and the max, I can use a bivariate transformation to get the order statistics of or get the distribution of the range by kind of doing a bivariate transformation, then marginalizing out one of my random variables. And we got at the end of the day that in this case here, that for uniform random variables, if I sample of uniform random variables, that the range has a beta distribution. So for example, if I were to look at the expected value of my range, you can look back in the notes about the facts, which is that the expected value of a beta n2 is n minus 1 over n plus 1. And so nicely, as n goes to infinity, this is going to converge to 1. Notice it's always less than 1, but as I get more and more samples, as my n, the number of samples I have, that goes to 1. And that makes sense, right? So if here's my possible range for my samples, as I draw a sample, right, the range is kind of the outer extent of my samples. So here, let me just draw circles as samples. So here's one sample, here's another one, take another one, another one. These are all uniformly distributed independently through this. And as I do this over time and I add more samples, the outer ranges of, that is the range of my samples is going to kind of monotonically increase to 1. So it's slightly less than 1, but will monotonically grow and grow and grow. And eventually, as I sample enough of these in the interval, I'll get a range that is really close to 1. And so that makes sense. We can say something more than just the expected value being kind of asymptotically 1, close to 1. Is that actually the range for the uniform random variables follows a beta distribution. The last thing I want to say here in the last couple of minutes, and no more examples, no more proofs, I just want to write one fact down. So we had talked about the marginal distributions of the order statistics. We had talked about joint distributions of the order statistics. And we could also talk about, you could talk about joint distributions of 3 order statistics. If you really hate your life, you could try and think about what that is. We could also talk about the joint distribution of all order statistics. That is, we could look at the PDF of x of the minimum and the second smallest one and the third smallest one all the way up to the maximum. And this is going to be, it has n, we have n different order statistics. First smallest, second smallest, third smallest, etc. So there's going to be, we can evaluate this as some number as u1, u2, u3, right, etc. Some dummy variables, doesn't matter. And you might think that this is a lot harder because we have n of these, look at how bad the marginal distribution of the order statistics was, then the joint was even worse. But it actually really simplifies when you look at all of them together. And so the joint distribution of all of the order statistics together is just 1 over, it's just the product of, it looks a lot like the joint distribution of the data. So if I stop there, that would just be the joint distribution of data. But what I do is I just multiply by n factorial. So it's basically the product of the marginals of the data times n factorial. Now, n factorial is basically that I can permute these things in many different ways. In n factorial ways, I could permute around my data and choose which of the x of I are the smallest, which of them are the largest, right? And so the joint distribution of all of the order statistics is really simple. It's just n factorial times the product of the marginal PDF f evaluated at each of the values I'm adding to my function. And so it actually works out to be quite nice. And that can be useful to know that actually it does simplify at some point. We'll stop there. We've done a real kind of deep dive into some statistical issues, some order statistics and things like that.